let me start. So the plan for today is to go through a little tutorial, and I assume that many of you already know BART, at least know what it is. So we will not give a complete BART tutorial, although the time is too short. But we will basically give a bit of an overview about what it can do, and also some new stuff we are working on to give you an impression what is possible. And the plan is that we have a Jupyter notebook prepared, which you can follow online. So if you go to the website of the BART workshop, maybe I will put the link also in the chat.
I've included it already in the chat.
Yeah, perfect. It's already done. Thank you. You can follow either using Google Colab, if you click on the link below, or Binder. Both should work, and I would ask you to basically click on this now, because at least in Google Colab it takes a little bit to set up. I will use that opportunity to give some introduction. And if you have BART locally installed, which is of course what I recommend to do in the long run, then you need a very new version, so you might need to update it, but it should be fine to use the Google Colab or Binder version for today. And right. In general, if we use BART, so BART was meant as a toolbox of many different little tools which can be used and combined in different ways. And I'm also very happy to see that other projects pick it up as a component. So if you have the Google Colab open, I ask you to already start maybe the first 5 cells, because this is a part which may take long. So Daniel, if you scroll up maybe again, let me talk about this real quick. So this is only setup part, which will do some setup for you, so that it also works both on Google Colab and Binder. We will use BART, for myself and my students mostly use it from the command line, and we will use the bash cells, which you already see here for the BART setup in this tutorial. So if you don't know bash, don't be scared. It's very simple command line tools. But I point out you can also use BART from Python or MATLAB. We have Python wrappers. You will not see them a lot today, but just point that out. If you look at other tutorials, you will learn how this works. So these first cells basically set up and compile BART, and especially the second cell, the make, which you can see now at the top, will set up BART in Google Colab. This is basically what you would also have to do locally if you install BART. It takes about 2 minutes to run on Google Colab. In Binder, it's already set up, so this may be a bit quicker. So if you run that stuff, basically, and also the next cell, which sets up some environment variables to make it version, you should be able to run this last cell you see on the slide today, and this should print out the version of BART you have installed, right? So with this, you would have BART set up and running, and maybe, I don't know, I'm not sure if you're following along. Is anybody running and doing that at the same time with us? Still running that? I don't know. Maybe could give us a hint in the chat if you need to wait a little bit longer. I ran it. Okay. Yes, still running. Okay. I talk a bit about what BART is, and then you can catch up so that before the real content starts. So BART is a set of command line tools. It has this main tool BART, which we can run here. We can run it in these bash cells in these Jupyter notebooks with the exclamation mark. And if you just run this BART tool, it will just give you an overview of all the sub-tools, of all the functionality which is there. And you can see we categorized it into different topics. And then we have very basic tools and very advanced tools for MRI calibration, reconstruction, and so on. We will introduce some of them today. But if you really want to use BART, of course, you should go to one of our basic tutorials to get the basic. But just to give you an idea, these tools always follow the same structure. So we have this BART command structure. You can see now at the bottom. We can scroll up a little bit, where we give the main BART command, and then we give the specific subcommand we want to use, for example, the FFT or PIX reconstruction, whatever. It typically has some options, and then we give it an input and an output. And these are basically files. So it reads an input file and produces an output file. These BART tools always have a little help. If you give the -H option, it will print out what it does, what input and outputs it expects, and what options there are. Right? You can see this now for the FFT tool. It can do a unitary or inverse FFT or whatever you want. It takes a bit mask. We will not talk too much about this today, but this specifies the dimensions we work on and an input and an output. Okay, so this so far is my introduction to the very basic concept of BART, just to give you an idea. And I will hand over to Daniel, and he will run you through some of the more interesting stuff, starting with simulation and sequences and reconstruction. And if you ask questions, you can do that in between, and either I answer them in the chat or we will address it here, discuss your points. And with that, Daniel, please continue.
Thanks for the intro. So usually, probably BART is a reconstruction toolbox, as the name says. But today we will start kind of different with a BART sequence. So with the new sec command. So with this sec command, we compute, in this case, or as a default, spoiled gradient echo imaging block. We define, for example, by the command and options, as mentioned, one radial line. We can set different sequence parameters as the echo and repetition time, and have as an output ADC samples, our gradients and moments. So let's look what is actually computed within this command. So therefore we can set the BART debug level to have more debug print and look at them. So generally we compute the block, and one sequence block typically consists or is described by a set of events. Each event has a start, mid, and end time. And we have 3 different types of events. So first one would be a gradient event with the respective amplitude on the axis. Usually they come in pairs. So we design a trapezoidal gradient with two triangles. We have an pulse, usually with our pulse has an additional frequency and phase information, for example, to excite slice shifted field of use. And we have an ADC event, also with an frequency and then phase information, for example, to have an FOV in-plane shift. The gradients and also the moments out of it can be discretized and sampled. And if we plot them, we see here now what we expected to see: a single acquisition block. We have no gradient on the phase encoding direction. We have here a readout dephaser gradient and readout gradient on the slice axis with a slice selection gradient and the slice rephaser. And by definition, we reset the momentum on the slice axis to 0 in the mid of the RF pulse. And if we now would look like how it's going with multiple lines and overlay it, it will just look simple. We have projection or rotation of readout and phase encoding to have multiple acquired lines in K-space. So the first output of the to to simulate or compute now a trajectory, a non-Cartesian trajectory, we can run the sec command now with a meaningful number of lines. We can define also a base resolution, and the first output would be the ADC samples. So we have with BART show -m, we can show them the dimensions of this file. We have in the readout direction 512, so basically the base resolution with an oversampling. We have our 377 radial lines or spokes, and in the first dimension we have 5, so we can extract the first 3 dimensions out of it as our spatial coordinates for the trajectory, and we have also additional ADC timing and phase, which we will need in a few minutes. So again, if we plot this, we see a huge number of different phase encoding readout lines. So we're sampling a full K-space in a radial manner. Now let's go to the simulation. First, we perform block simulations for different tissues. So in this example, we vary the T1 values here with this flag from 0.1 to 2 seconds for 11 different signals or tissues. And we define for our block simulation a flash sequence with the before described sequence parameters. In order to have a sufficient T1 weighted contrast, we acquire multiple repetitions to arrive in a steady state and write this to the this output file. And with this command, we now can, or with slice, and we can extract the last repetition out of it to have like 11 different signals. And with the phantom tool, we want to now create the full numerical phantom with these 11 different tissue types and signals. For more detailed intro, I would refer to the 23 secret session on digital reference objects. But we use basically the phantom tool with the -k flag to have to generate a K-space phantom. -t just tells us that we want a tube phantom, and -b flag sets us that we have an output basis geometry with our before sampled or computed trajectory from the sequence. If we combine now the basis geometry with the simulated signals, with our numerical simulated K-space phantom, with a simple recon, so with just a single coil, we can perform a non-uniform inverse FFT. We can generate or reconstruct our K-space phantom, and more closely you can see with some ringing artifacts. This is a K-space phantom. It's an image phantom. What also is an output of the sec file or the additional dimensions of the ADC samples would be the ADC phase. So if we now include an in-plane FOV shift for the sec for our sequence and extract the ADC phase, multiply it with our simulated K-space, we should obtain an off-center simulated or field of view shifted K-space, which we can compare now and see that we have shifted our field of view basically for the phantom. If we want to try to estimate the rigid body motion, we can use the affine rec tool on our image and the image and the off-center image to obtain the affine transform matrix. So we can again see that we have in the last dimension 0.05 and 0.12, which is exactly the same as we before simulated for our sequence. With the FOV shift tool, we correct the translational motion by shifting the FOV retrospectively. So this is just a multiplication of the phase on this off-center K-space to correct it, reconstruct it again with the same non-uniform FFT, and see in the difference map that we also corrected or fully corrected the FOV shifted phantom. So this would be the first part on sequence programming and just some simulation. But what about Recon, the BART working horse? And for that, would like to create an undersampled non-Cartesian multi-coil phantom in K-space. So we can again call our BART command now with fewer number of radial spokes, and extract again the trajectory. We simulate again in K-space phantom, same as before, but now with additionally setting the number of coils with the minus, with the S flag or with the S option. They have a new basis geometry now with multiple coils. And if we combine this now with our 4 calculated simulations and print now a multi-channel K-space phantom, we have basically now included all of the 8 channels in one image. We show it and have 8 coils. So after creating this undersampled data, we can again perform a non-uniform FFT and root sum of squares coil combination. So there's a simple RSS reconstruction, which is of course not very good. So the image is corrupted with noise and some residual streakings from the undersampling. So let's start with a more advanced reconstruction technique. Therefore, we have to first estimate and determine the coil sensitivities with the end length algorithm. So with the NCalib tool, and NCalib tool just needs as an input the trajectory and our K-space, which is just simulated. So it would be an simulated or acquired K-space, and as an output our sensitivity maps of this phantom. Given now this coil sensitivity is S, we can perform an iterative parallel imaging reconstruction. So we want to minimize the following problem. We're minimizing for unknown image X, multiply it with the before pre-computed coil sensitivities. We have the Fourier transform and the non-uniform sampling operator, which we want to minimize to our acquired or simulated multi-coil K-space data Y. Picks as an option for a variety of regularization terms, but in this case we will use an L1 wavelet regularization. So what options do we need basically for the parallel imaging compressed sensing reconstruction? The first one would be the L1 flag to set the regularization term. We have a regularization parameter lambda, which is set with small r. We scale our step size based on a maximum eigenvalue with E, and also can select our maximum number of iterations for the recon. So we now provide our trajectory as a part of, as we think of the equation PF. We have the acquired or simulated k-space y and our sensitivity maps S to obtain an image X. And this, if we compare it now to the before mentioned RSS recon, we see a substantially improved image quality for the sense reconstruction. So we have a sequence, we can simulate it, we can reconstruct data, but which is highly desirable would be, can we also acquire data and validate our simulations, or can we predict what we want to acquire with our simulations? And therefore the sec command has also an fourth output with for a pulsec file. So with the .sec would be the pulsec format. And if we calculate it now as an example for 3 radial spokes, so we define here and check the sec file, or the first lines of the sec file, one would find pretty familiar definitions for the scanner system parameters, and also the pulsec standard in a blocks format. Each block consists of an RF excitation. We have gradients and ADCs, and was also included here after when generating this pulsec sequence file is the command that was used for the generation of the sequence. So this allows us to fully reproduce the sequence which was used in the acquisition process. And we can now install our PyPulsec Python package, which I've done before locally, and plot the sequence. So one can find pretty familiar plots from the PyPulsec plot command. So we have the ADC, we have our sync-shaped excitation pulses. We can validate that we have the same RF and ADC phase, and again our free access for the gradients. So the first one in the first block without any gradient in the phase encoding direction, the readout, and the slice gradient multiplied by 3, since we want to acquire 3 spokes. For a meaningful acquisition, we now have to just adjust our number of radial spokes. We can play around with our sequence parameters, which are fairly all available through the command line options, and export our sec file. With this sec file, one can go to the scanner and use the widely available pulsec interpreter sequence, load this sec file, and acquire data. And I'm going to check the time. I think we have time. It's a bonus for the recon of data acquired by the scanner. Sorry?
Yes, yeah. I think we have a bit of time. I could go that.
Perfect. Yeah. So we have done that in advance, because otherwise it would be we would not have time to go over it. But we've acquired data with the sec file. We've also acquired a noise scan, so single acquisition without an without an excitation. You can use it. You can use BART Twix read for our DAT files, which I've done before already, and provided you with the K-space and the noise data within this notebook repository. So from the dimensions, we can infer that we have again our 512 readout samples. We have the 377 lines, and there are 16 coils. Similar or analogous for the noise adjustment scan, which is basically an Cartesian scan. So we have 256 in the readout dimension with just a single phase encoding line. Again, the 16 coils. We can also plot or show again the quiet K-space. And what we have done, or what is a good idea to do before reconstruction, is noise pre-whitening. You can check the pretty old intro Michael Hansen, but I think it's not outdated. So let's check first the noise covariance matrix. You see it's not really uniform, so have different noise levels across the coils. And what is desired is quite a unit matrix for the noise covariance matrix. Here we can use the BART whiten tool. First, we want to whiten the noise data by the noise data itself to have a validation step and see a unitary matrix. So we use the whiten tool on our K-space. We perform a noise pre-whitening on the K-space as a first pre-processing step. For the reduction of the dataset and decrease the computational complexity, we perform a coil compression with the CC command. So with the CC command, we can output a coil combination matrix. And with CC apply, we can compress our whitened K-space to 8 virtual coils. So we now have only 8 coils instead of 16. Each of the coils with the decreasing energy across the coils. As shown above, and what is now relevant for reconstruction retrospectively, is that we have saved our sec file, which we want, or which was used for, or the command to generate the sec file is saved in the sec file used for the acquisition. So we can just copy it again and regenerate our trajectory out of the recovered or reproduced sequence. With this, we can perform a gradient delay correction with the ring method. Again, estimate our coil sensitivities with the NCalib tool. Obtain our 8 virtual coils and use a PIX reconstruction again with an L1 wavelet similar to the before simulated K-space. And in the end, can show that we've sufficiently reconstructed our acquired K-space data with this pipeline.